All right, ladies and gents, welcome to flipped classroom kind of teaching. It's a good way for me to make sure that I'm still teaching you even though I can't be with you today. So the first thing I want to go over with you today is how to predict products. And the reality is you already know everything that you need to know. I'm just going to break it down stepwise with you and run through a couple of examples. After that, we're going to talk about something called the activity series. We'll practice that, and then you guys will be set free to practice in Steve for the rest of the block. So on your screen, you should see some slides. These are in that Pear Deck from earlier this week. The first step to predicting a product is just identifying the type of reaction based solely on the reactants. So if I look at the reaction on the screen, I see that I have two reactants. This disqualifies decomposition, right? Because decomposition is only going to have one reactant. So then I look, could this be combustion? Do I have a hydrocarbon and oxygen? No. So I have synthesis, single replacement, and double replacement left. It's not going to be single replacement because I don't have a lone atom. So now I'm down to synthesis or double replacement. This technically could be a synthesis reaction, but my product is going to be insanely massive. And hopefully you can recognize that this has the characteristic shape of a double replacement reaction. I have A, B, plus C, D. So from there, I'm going to look and figure out the general shape of my products. Ooh, that should say products right here. I'm going to change that to products. So the first thing I've got A, B, plus C, D. And I know in a double replacement reaction, right, they're going to switch partners. So Al is going to be left with sulfur, and barium is going to be left with chlorine. Notice I said barium with chlorine, not chlorine with barium. Take a second, pause the video, think if you can figure out why that is. So hopefully you actually paused the video. That's because we know in ionic equations, which is what this is, right? This is ionic bonding. My cation always comes first. So when barium and chlorine bond together, I'm going to write the formula as barium chloride. So once I know my general shape, I'm going to actually write the formulas for my products. Remember, this has nothing to do with coefficients. We're going back to ionic formula writing and we're just working with the charges. So to review very quickly ionic bonding, you've got aluminum that has a +3 charge, now bonding with sulfur with a -2 charge. So if I crisscross the charges, that leaves me with aluminum 2, sulfide 3. Oof, that's dirty. Sorry about that. And then barium has a +2 charge, and chlorine has a -1 charge. So if we put those together, I'm left with BaCl2. I think my pen's running out of juice. So now that I've got my products written and my equation, my individual formulas to neutrality, now I'm going to balance my equation just like I've always done. So I've got 1 aluminum on the left and 2 on the right. That looks like 12. That's confusing. I've got 3 chlorines on the left and 2 on the right. I've got 1 barium on the left and 1 barium on the right. And I have 1 sulfur on the left and 3 sulfurs on the right. So what I want you to do, take a second, pause the video, see if you can balance this equation on your own now. So hopefully your reaction looks something like this. I've got 2 aluminum chlorides plus 3 barium sulfides to produce 1 aluminum sulfide and 3 barium chlorides. So now if I check, I've got 2 aluminums on the left and 2 aluminums on the right, 6 chlorines on the left and 6 chlorines on the right, 3 bariums on the left, 3 bariums on the right, and 3 sulfurs on the left and 3 sulfurs on the right. So everything left and right is equal, which is what it means to have a balanced reaction. So we've done all the steps, right? We have officially and successfully balanced my equation. And you just want to, this step 5 is actually what I did in step 4. You know me, I like to rush. I made sure that I didn't have anions with anions or cations with cations before I did the balancing part. So far we've been living in like blissful non-reality world. We've assumed that every single chemical reaction that can occur on paper will occur in reality. And we know that that's just not factually true. We know that while there are tons of reactions happening all around us, not every single collision results in a reaction. So the 2 that we're going to learn specifically about this year is single replacement reactions and double replacement reactions. We use 2 different tools. We use an activity series for our single replacement reaction and a solubility table for our double replacement reaction. And today we're just going to focus on single replacement reactions. This is what an activity series looks like, or can look like. You have one on your purple reference sheet, which hopefully you got. It's on the bottom. And this just tells you how active a metal is. The more active the metal, the more reactive the metal. The more reactive the metal, the more it's able to do reactions. So if we look over here on the right, you'll see 2 reactions in green and 1 reaction in red. Take a second, pause, see if you can figure out what the difference between those reactions is using the tool on the left. So, hopefully you did. Hopefully you figured it out, but if you didn't, I'm going to walk you through it. If we look at this first reaction, magnesium is here on the activity series, right below sodium, 4th in the line, and mercury, Hg, is all the way down here at the bottom. So mercury is more reactive, magnesium's more reactive than mercury, which means it's going to be able to come in here, bump mercury out, and steal chlorine as its partner. If we look at the second one, copper versus mercury. Copper's right above mercury in the activity series. That means it's still more reactive than mercury is, so it's going to be able to come in and bump it out. If we look at the last one, silver. Silver is below mercury on the activity series, which means it's not reactive enough to cause the bond between mercury and chlorine to break or to be more attractive to your chlorine ion so that chlorine wants to bond with it rather than mercury. If this is the case, no reaction occurs. So the next 2 slides are kind of just reiterating what I've already said. I'm going to put them both in the video, that way you can kind of pause the video and take a look at them if you want to, but I'm not really going to speak to them in this video. So I'm going to do 2 practice problems with you, and we'll go from there. So step 1 is the same, right? We've really only added 1 tiny step to our process. Step 1 is the same. Identify the type of reaction based on the reactants alone. Here I have 2 things that are bonded together and 1 singleton. The only reaction that looks like that is single replacement. Now we've got a step 1.5. If it's a single replacement reaction, we have to determine if this reaction will actually occur. So if I look at this, the question is silver, my lone element, higher than magnesium on the activity series? Here's silver, here's magnesium. So the answer is no, it is not higher on the activity series. So this is really, really easy to move forward. If it's not higher on the activity series, you literally get to say no reaction. You don't have to write the products. You don't have to balance the equation. Your job is done. Okay. Second practice problem. Hopefully at this point you can guess how this one's going to go. So we're practicing again. I have magnesium chloride plus potassium, right? I've already identified that it's a single replacement reaction. Now I'm testing to see if it's actually going to occur. Here we have potassium at the very top of the activity series. It's going to replace anything if given the opportunity. So this will occur, so I have to move forward and actually write my products. Next step, what's your general shape? Is potassium going to come in and replace chlorine, or is potassium going to come in and replace magnesium? Hopefully your answer was potassium, right? So now I know my general shape and I can come in and actually write my formulas. Potassium has a +1 charge, and we know it's going to be bonding with chlorine, which has a +1 charge, so I just have potassium chloride. And then magnesium is going to be left all by itself as a metal, no charge, no coefficient, no superscript, no subscript. And then from there, we just do another check. Did I make any stupid mistakes? Do I have any weird things bonded with one another? No. I've got cation and anion plus a metal to produce a cation and an anion plus a metal. So from there, I balance, right? Hopefully at this point, you're starting to be able to balance some of these without making your list. If you need the list, that's fine. Go ahead and make it. Here I see 2 chlorines on the left. So I'm going to add a coefficient of 2 chlorines on the right, which up to my potassium number, which means I need 2 chlorines on the left. That's Reese's. That's my Christmas tree.